just trying to start up my Kindle as I wanted to show you some of the reference material that I've been using for this course. Okay, fantastic. So anyone interested, there's what's called a canonical hypergraph. I wonder if any of you have seen that, or I'm sure not many of you have used it, but that's part of the canonical model for integrating data. But this is a book that I've used as the background, almost the theory behind conceptual modeling. And what I liked about this is, can you see here, there's structural modeling, process modeling, user interface modeling, and then special challenging areas, for example, the GNOME project and spatial modeling and different areas like that. So can you see conceptual geometric modeling, migration, data integration using the canonical model and ontologies. This is the web of knowledge, which is OWL. And so there's a lot of detail around that higher level of modeling, or the sort of the modeling that Maria Keats was referring to. Okay, now I really got a lot out of this reference material in sort of setting my mind right from what is a conceptual model, what is a conceptual data model, and then what are the other forms of conceptual model. And you may have been with us on the previous week where we even showed you that electronic circuit board is a conceptual model. Okay, so we can build conceptual models to communicate our understanding and the understanding of the way in which the system works. And it's helpful to understand the role that conceptual modeling plays. Okay, so just to go back on the learning path, we started off with the data manager. And what was important to the data managers in setting up an implementation framework, the ability to scale in adaptation to evolving business needs. And what we spoke about quite a bit there was the fact that we must always remember that data modeling is one aspect of all the modeling. So what about the business process modeling? What about the user interface, the application, the system modeling? All of these we need to be aware of, and we need to know how they relate to each other. And I'm sure you may have seen me present the Zachman diagram in terms of, we talk about the vertical decomposition of the what area in Zachman. So we go from subject area model, conceptual, logical, physical, implementation. But many of those models are conceptual models. Okay, so all of those models there, other than when it sort of gets into code, then it's moved out of the realm of conceptual modeling. All right, so that was part of the data manager, and what was important there was how dependent and how much conceptual models can help data governance. Everything from business glossary definitions, data models, subject area models, operating models. There's lots of relationships between the two. Okay, so that was the data manager. Then we got into the data citizen, and I tried to, and I felt like I didn't do a very good job of trying to explain to the data citizens how to read that threefold mechanism of, there's what the origin looks like that the users have in their minds. That's the origin that we come from. And then we build a model of that. And that model is governed by a language, a conceptual language that governs the model. Okay, so what we have to do, first of all, to allow our citizens to read the model, we have to explain the language. So that's what we refer to as the literacy of how to read a model. Okay, and then what I suggested is the way of learning to write would be, how do you read a model, and then how do you check for the quality of the model, and then once you know what a good model looks like, then it's a lot easier to build a model or write or create a model. Okay. Then about how do we get adoption in using modeling for decision making? We're going to go a lot more technical today. Simplification of that origin. When we look at the origin that we want to build a model of, these conceptual models are normally focused on the core concepts. It doesn't deal with everything. The model will take too long to build. So we have to be very careful of trying to model everything. So there's certainly, we balance between simplicity and complexity. Those are the balances that we must pay attention to. Okay, so that was the data citizen. And this is the appropriate areas. How do we get conceptual models to make informed data-driven decisions? Okay, now today we're going to focus on the data professional. And there are some challenges in terms of how do we get and enforce the model accuracy? And maybe just to pause there, has anyone spent any time reviewing data models, trying to confirm that this data model is the appropriate reflection of the real world that we need at this point in time? Can anyone share a story or a challenge that they faced in doing something like this? Yes, Don.
Thanks, Howard. In our world, we use different phrases and
Yes.
for these concepts. So, I'm interested in learning more about the way that you as data managers think about these concepts. But speaking as an economist, our use cases generally involve making sure that once that data that's been taken from somewhere and moved along a pipeline,
Yes.
it might have different vintages of the same data, may have been transformed a couple of times, or used in different processes. And so there's a validation process which we go through to make sure that either that if it's lineages of the data, that you understand how large the changes have been, the revisions have been. If it's the same data that's just been moved from one place to another place, then there's a validation process to make sure that the data is unchanged, or that if it's an update to a data set, that the data there's continuous, that the data is continuous, that there isn't a break in the data, and that the update is sensible. So that's one kind of practical example. Another would be that the definitions are met, so that that the metadata, that the data is consistent with what's described in the metadata.
Right.
And then maybe one last example would be, and I'm just thinking off the top of my head, deeper statistical validation of the data. So we deal a lot with published data from official suppliers, but the data could still have some statistical anomalies in it. And the tricky thing there is that sometimes economic data or financial data have genuine statistical anomalies, and sometimes so there's always a sense there's some of these that you can identify programmatically, and then there's some of them that require deep specialist checking. So maybe just one example would be, if it's trade data, the country may have imported a frigate, and so there's a very unusual spike in the trade data from some very, very unusual transaction that an expert would need to validate. So those are three examples.
Okay, and that last one is typically that outlier, and you can't just remove or filter out the outlier. You have to check to see whether it's actually real, and you have to confirm that. So thanks, Don. Now, a lot of what you're referring to is what we would call the quality of the instance data, the data that's sitting in the database or the data sets. Now, the model we're referring to here would I think, to relate to a statistical side. As an example, if you were to build a model of the features of GDP and how they relate to each other, it's that high-level model that we use in terms of how do these core concepts or core features of the GDP work together, and what's their relationship between each other. And you'd probably build a high-level conceptual model, and then when it comes to the determining and interpreting the statistics or the data around the GDP, you would then build a visual representation of that model. Yes, Don?
So maybe an example, a tangible example would be in the case of consumer prices, there are official weights.
Yes.
So you've got a hierarchy, well, not a hierarchy, but a certain set of data series that have assigned weights that then comprise the index.
Right, right, yes. And that weighted average that model of how that weighted average is working, that's the sort of model that we would look to. That's one of the models. Now, so a conceptual model is not just a visual model. It can also be a word model of how the things relate to each other. But the important aspect is the relationships between those core concepts. Don, does that make sense in terms of how we use the word conceptual model?
That just sounds interesting. I'd love to see what that actually looks like in practice.
Okay, great. And we're going to go through some of that now. So that's what I'd like to just make. We're all data people, but it's so important to understand that conceptual models are there to simplify, they're there to present, they're there to communicate the way in which it works. And Maria Keats, in her webinar, she actually presented a really interesting one about the runoff of rainfall water on a mountain, or biology concepts and things like that. So academics, scientists, or whatever it is, they build a model to try to explain to people how the thing works. And these models can get very complicated, but they are typically visually there. Okay, so now what we're doing is to say, well, we've built this visual representation, but how accurate is it? And we know we've already done some genericizing or whatever it is to filter out the key focuses. Then now, how accurate would something like that be? It's a very important point. That we people, in terms of data governance, whatever you're involved in, you need to know how to check the reflection of the real world. Okay. We're then going to talk about compatibility with other areas like linking to master data, data analytics. When we build a model, how do we do that? How would we create a wide data set from our data model? How would we extract it into a wide data set for goal seeking, or correlation versus causation of different features within the data set? And then we talk about continuous improvement. What does a conceptual modeling playbook look like? Advanced techniques for data analysis and design, best practices in terms of how effective models that accurately reflect business needs, and then explore conceptual model usage. So those are the things that we want to tackle today and go through with you. Okay, and then next week is going to be for the executive. So how does this conceptual modeling get presented to the organization that they would want to spend time on it? And I think this is an important point where we've been failing. Lately, data modeling is not a big thing. So many times the programmers are saying, why do we need to do this data modeling? It doesn't really help us. And we have to try to justify why we must spend this time. And it would be up to the executives to ensure that we get buy-in from the top stakeholders, and then it comes down. There's no use having 100 different arguments at the lower levels with the Java programmer, or so C#, whatever it is. That's not the place to have the argument. It's to be able to justify that we get better insights, decision-making, and alignment. And that's the next week one. Okay, so here is the conceptual model, and I'm sure you can see it growing, and we have to go through quite a few elements today. Now, we've been through the terminology, we've been through definitions, we've been through the characteristics of a conceptual model. And maybe to explain to Don, this may help you, Don, there's a data modeler, and a data modeler gets given a purpose by a data consumer to create a model of the origin. Okay, so the author would spend time collecting the right stakeholders together in a workshop, and they would observe the origin. What are the core features of this origin? The origin could be anything. It could be a real world environment. It could be a set of business processes and procedures that they're building. And through this observation and understanding the consumer, they develop a model that represents the origin and communicates to the consumer that you first of all got the ideas from, who was properly the subject matter expert, and then all other consumers. Now, other consumers' examples may be the programmer that needs to implement this. They would say, right, there's the business requirements have been extracted out of Word, they've been put into a model, and now I have a model of how my program needs to work. Now, as I say that, I'm sure you're starting to ask the question, well, a lot of the modeling we've been doing, and Adam was saying that, he talks about ORM modeling and ERD modeling. Now, that focuses on structure. Okay. Now, what about the behavior of the system? A state diagram. What states does the system transition through? What are the actions that the system must respond to, or the events that happen? And Don, I'm thinking of the models that you produce in terms of shocking the system. These are sort of events that come about, and you would play those models, or you would play those things through the system, and you'd see how the model responds. Okay. So that's one of the areas. Okay, so that's sort of the characteristics of a model. And then what a manifesto, there's actually a conceptual model programming manifesto. And the manifesto is pretty simple. And basically what it's saying is that all programming activities can and should be carried out completely at the abstract level of conceptual modeling. Okay. Now, when I looked at this thing, I said, sure, I haven't seen that actually work. Lots of people have tried to get it to work. I don't know if you ever saw case tools and case modeling that they tried to get this to work. I've never seen it work. And that's probably why we battle so much to validate the accuracy of our models. Now, if, let's say, we could get it to work, it would be rather easy, right? You build a conceptual model, you convert it to code, you then run the program, and see whether it's actually working or not. Has it translated appropriately? Okay, that would be a relatively easier way of doing it, but almost the semantic gap between the language, the model, and the application, there are gaps there. And so we can't always convert the model to the application code. Okay, that's sometimes referred as a semantic gap. So, but they still feel and they still hold to this thing of the conceptual models should be able to do it. Now, a lot of the times what I've been unaware of is there's actually something called a object constraint language, which defines all of the constraints and the relationships, and it's almost looks like a set of code, and that's a lot of the times what a ontology is getting to, is these constraints and mathematical logical decisions that can be made within the model. Okay, model-driven software. Okay, these are software models, must go beyond blueprints, mere blueprints. And I believe that's seriously where architecture and data modeling have been almost pushed to the back to say we no longer need you. Okay, we will just write the code, You give us the requirement, we design the screens, write the code, and then we'll almost reverse engineer the data that we've been collecting, and then we'll be able to show the business people how to query the data, or how do we get it out of a JSON document into a data warehouse so we can start building analytical reports. Okay, so the other aspect is constitute the basis for automatically or semi-automatically generating the software system itself. Okay. Have any of you been involved in that case engineering approach where they try to do this? I was involved in one or two, and they've all been failures. So it would be nice. I'm not sure if anybody else has. Okay, sorry, Don. Okay, so this is the manifesto. This is what academics and it was actually quite interesting to see Maria Keats' blog page where she actually talks about designing an ontology or a language specific for your conceptual model, and that's the sort of thing that can be used to generate an application. Okay. All right, so now let's take a look at the different modeling languages, and there are lots of modeling languages. And maybe just to take a step back, these are the spectrum of models. So we can have sort of code only, where there is no model, and that's a lot of what some of the latest Agile looks like, is let's go to code, let's write the web page, we save it away in a JSON document, and then we maybe reverse engineer the code. Okay, so can you see here, there's this almost code visualization where we take the code and we build the model of the code or the model of the data. And then we also get round trip engineering, where we create the model, it generates the code, we may go and change the code, and then we reverse engineer to the model again. Now, there was a demo by Marco Woben on Case Talk, and I don't know if you remember. What he would say was, here is his data model. Even if he goes into the database and does an alter on a field or whatever it is, a constraint in the database, that could be reverse engineered back into his Case Talk model, which is great. I mean, that round trip engineering is almost a must these days, because when you get to semi-automatic, as soon as you generate the database and you go and change the database, if the model is not kept up to date and you drift, you have this model drift or code drift. When you come back to the model, you say, this does not reflect the code that I know is there, and you'd actually go and throw the model away and then re-engineer it again. Then we have model programming, which is basically what I've shared with that vision, the manifesto, that the model generates the code. So the model is the code. And then, of course, we have model only. That's almost that biology model, right? It doesn't generate any code. It's really just talking about the dynamics and the way in which the system works. The system may not be code. So it's about doing the design. So there's the spectrum that you have. And here are the languages. So we have languages that talk about foundational concepts, almost the words and the language that we talk about, and that can be brought about in terms of taxonomies. Remember, we have the taxonomy, the hierarchical taxonomy, that does a broader and a narrower concept, and it structures concepts together. So, for example, the animal kingdom at the top is an animal, and then we break it down into the different types of the species, and we get narrower and narrower definitions of an animal, but they can all roll up and down depending on what level of information you are looking at or what level you're working with. Then we have what's called declarative languages. That was part of Maria Keats' discussion on declarative modeling. So here we go. We've got entity relationship diagrams, CHEN, IDFEX, IE notation, dimensional modeling, fact-based modeling, ORM, and then we've got cumulative object modeling, time-based modeling, and I'm going to show you some examples. Then we've got representational languages. Okay, ontologies, graphical visual languages. There's UML coming in. And then we've got textual representations and Z. And interestingly enough, I did my master's degree on the Z notation using that language. It was basically a language that we use to describe state machines. So if there was a behavioral system, you could describe that system entirely using the Z notation. And that's the one that I did my master's theory in electrical engineering in the Z language. So that was it's lots of mathematics and lots of being able to express everything in a set of mathematical terms. Then we go to programming languages. They call it declarative output languages like SQL, and then imperative languages, procedural, C++. And then we get into integration. And these are other languages that we can use. Okay. So there's a whole range of different languages, all stemming from and are riding around the conceptual modeling language. Now, to try to show you why UML is so different or is so important to us, is you can see that they have their models or their diagrams break up into structural diagrams and behavioral diagrams. And our data predominantly sits in this structural diagram in terms of a class diagram and a composite structure diagram and a package diagram. These can be package diagrams of data products, of subject area models. This is all about the structure. How do we structure the domain? Okay. Now, UML introduced a behavioral diagram. Okay. And that's where the application comes in. So this is where we need to be clear with the application developers how we're using this data. Okay. Now, the nice thing about UML is that if you have extensive object-oriented developers or coders that are going to write code against the data, you want to make sure that these two can be used. Class diagrams, database tables, they must all come off the right set of diagrams so that when we have an activity diagram or an interaction diagram or a use case diagram, this is how the system works. It should be working off our data model, and we shouldn't have these discrepancies. Now, that's the problem that you fall into with an ER diagram. It doesn't have the corresponding behavioral diagram. Okay. And to pause there just to see, do people understand why these two worlds have to come apart? So the ER diagram suffers tremendously from this lack of actions and events. Okay. It just focuses on this area over here. All right, and then in the de-embark, they use this term scheme and notation. So basically, these are the different modeling schemes: relational, dimension, object, fact-based, time-based, and there you can see the different languages that I've presented. Now, the actual what we can see here is what the de-embark has got here is incorrect. So when there's a NoSQL, and that's actually a type of database, this is not a language. A document is not a language or a column or a graph. It's really just a storage mechanism or technique that we've used in the databases. Okay, so it's important to remember it's not a notation. It's just a different type of NoSQL storage, or lots of people call this a non-relational storage system. Okay. So what we need to be careful of is when we choose the database schema, we must understand what is the best structure that we use to reflect the data. Okay, so if we're coming off an ontology, okay, the best structure for an ontology is a graph structure. Okay, it's not a relational database. Yes, you can almost downgrade the ontology to a relational database, but you lose a lot of the semantics and the meanings that have been defined by an ontology or a vocabulary. And I'm going to give you some examples of that as well. So these are the factors that you need to take into consideration when you decide on what database schema should I have. Okay. and we were talking about the schemas over here. Okay.
So Howard?
Yes, Paul.
Just a quick one on NoSQL.
Yes.
I mean, might be obvious to others, but
no, don't worry.
So you're right. I mean, this document is not a notation.
No,
so you don't actually, you can't model NoSQL, right?
You don't. It tends to be a physical implementation language.
Yes, it's not you don't model it. You can't. It's a physical implementation so that you can handle what you don't know is coming in, right?
Yeah, correct. And I'm actually going to show you an example, Paul. But that's a great question, and I'm sure you've battled to explain some of these things.
I did
in your data modeling course.
Now I don't have to battle anymore.
Okay. All right. Great. Okay. So let's go through it again. Now, also, please remember that these are all conceptual models. Even the physical data model is a conceptual model. That's not the instance at that point in time. It's actually a higher level representation of the database schema. Okay. So these are the different things that we need to pay attention to when we're choosing the right model and the right database. Okay. So, for example, if you're choosing a JSON document, don't think you're going to find a JSON conceptual data model. Okay. That's not going to work. And you see all of the NoSQLs are sitting at this physical data model implementation. Now, the nice thing about a relational model, because it's there to describe the business rules and the core business concepts, it can be used as a higher level model for all of the database storage types, from relational to multidimensional to object-oriented storage systems to a document to a graph. There you can see it. The conceptual models can describe what's there, what exists in that database. And I'm going to give you a nice example of that. Okay, so let's jump through some of the different types of models to answer Paul's question. So here's an entity relationship diagram. This is the person. Peter Chen was one of the first person that wrote a paper on entity relationship diagramming. Okay, he built this language that he has, and we would recognize this as normal ERD modelers. Can you see there's an entity, employee, and there's a department and supplier and part. Now, that when it has a double border there, that means it's a dependent entity. Now, these diamonds represent relationships. So you can see here we've got different types of relationships between employee and project. We can have this employee is working on the project, or this employee is the project manager of the project. So there are different types there that come in. And then you've got this many-to-many, one-to-many scenario that you're playing out in the original Chen diagram. Now, when you extend the Chen diagram with attributes, can you see here that they actually show you a representation of all of the attributes plus the type of attribute? Okay, so there we go. Now we've got extended with attributes, which is, now we would know that as a logical model, or Diem-Bok refers to this as a logical model. Then along came the UML. This is plain UML. We also sort of understand this. There's an entity or a class or a table with the attributes, and then it has relationships. Now, the interesting thing about UML is that it actually goes into the relationships are a lot broader than what an ER diagram has. So it has aggregated relationships, it has composition relationships, it has association relationships, has all of these different types of things, and they are more complex. The UML is more complex than your normal ER diagram. And then here's a way of describing generalization in UML. And you can see here there's disjoint and overlapping. Okay, so basically what it says is that you can't get any more than so the individual elements, okay, they are the full superset. Okay, and you can see them. We basically have female employee, male employee. You can't get anything else. There may be some arguments these days about whether, but let's not go down that route. So you have disjoint complete, you have disjoint incomplete, meaning that there may be more. This is just a sample of the subtypes. And then you get overlapping incomplete, so that there may be someone who's both French and Italian. Okay, and then we have overlapping complete, which means they are distinct. So typically you won't have ground staff that is flight staff. Okay, so there's lots of things to take into consideration here when you're doing the modeling and you're modeling the subtypes of an employee. Okay, so some important elements. Now they went along and they created an extended ERD. Okay, so I'm sure you can see that this is getting a whole lot more complex, where you have all the different inheritance types and you've got the attributes. And so what they did was they basically saying the ERD language was too restrictive. Okay, it had certain limitations. And so they created a new language, a new conceptual language to explain an extended ERD. And here you can see they've taken almost the aggregation to another level that wasn't part of ERD, but is part of UML, but people wanted to stick with ERD diagrams, so they extended it. They extended it to complex attributes, calculations. Can you see the rules that are coming out here? How do we calculate something? And I wish Don was here, because this is where we're getting into some of those models, that currency rates and exchange rates and things like that. And then we've got what we call participation, mandatory and optional. And that also talks to the cardinality and optionality. Okay. So they went ahead and they extended the ERD diagram. All right, dimensional modeling. I'm sure you guys know a lot about that. There's the conceptual modeling. I'm not too sure how many of you are aware of this, what they call the peacock diagram or the axis notation. And this is a conceptual way of reflecting the grain of a dimensional model. Okay. Yes, we could reflect it like this, and then the business person would have to be very savvy to say, these are the dimensional hierarchies. It drills down from year to month, and then it connects to the order, and it doesn't have a day. And we have a product hierarchy, which goes from category to line to product and connects to order. So this is a way, because why is this diagram so important? Because the grain of the dimensional model is the weak spot in dimensional modeling. Get your grain wrong, and then you get users that are very frustrated. They want to drill down. For example, this one over here. How do I drill down today? Okay, I need to see a day here, but you've just given it to me in a month. That means you've got aggregated data and I can't get the right detail. Okay. All right, now we go to what's called focal point modeling. And I'm going to try to give you some examples. So the first one is data vault modeling. Okay, can you see there? Hubs, links, and satellites. Now the hub is a core concept. That's an entity. But the nice thing about the hub is it only has one attribute, and that is the customer code or the customer key. All the other attributes are separated out of the hub into satellites. Okay. So the nice thing about that is all you need to get a customer into the data vault is the code. Okay, you don't need anything else. You don't need the names, the ID numbers, and things like that. So you don't have problems with getting a new customer registered in a data vault data warehouse. One part of the reasons why they created it. And then there's the relationships between a hub and a customer and a product. There's the link, and there are all the details about that relationship. And then we have orders. So that's what the data vault looks like. What is important to remember about the data vault is that it's separated into a raw data vault and a business data vault. So all the data comes in and basically is integrated in this raw data vault. And then the business data vault is more of a conceptual collection of the data coming together. Okay, and then it goes downstream into your star schemas, into your normal dimensional modeling. So Data Vault has not removed dimensional modeling. but it's just over here. Data Vault actually replaced the enterprise data warehouse or the third normal form relational database. That's what it replaced. Okay, then we have anchor modeling. This is your sixth normal form, Paul. I wanted to show you that. So the anchor modeling is taking it to a sixth normal form. Why is it in sixth normal form? Is because every single attribute is a table. Okay, can you see here? There's a program, but it consists of a name. Okay, and it relates to a stage, and a stage has a location and a name. Okay, now a historized attribute means that the stage could have changed names. So from this date to this date, it was that name, and from that date to that date, it was another name. So they also deal with what they call time-based modeling. Okay. So Paul, can you see what a sixth normal form database looks like?
Thanks, Howard. Yeah, sure.
Now, one would ask yourself the question, and especially if you've done the data modeling exam, they talk about we denormalize for performance. And here we've gone and normalized to the nth degree. You can't normalize anymore. It's just impossible. So what would be the benefits of something like this type of model? Can anyone share why would we go this far? Okay. Takers. So the best thing about this model is that the model will never have to be changed. So once I put these anchors, attributes, ties, and knots, I will never have to come out and then say, oh, shucks, but the attributes in program are wrong. They should be name and surname. Okay, no, surname is just another table. So we'd create a surname and we'd link it to the program. So it's referred to as an additive model. Okay, it keeps on growing, it keeps on extending. You'll never have to bring the system down to change it. Okay, you can just keep on adding, and you don't have to go in and break something and say, no, this doesn't work anymore, let's restructure it. And of course, that's where relational databases suffer. They are so hardwired that to make a change, you've got to bring the database down, you've got to regenerate everything. And that's what led to things like NoSQL databases because of those challenges that we faced. Okay. Now, then we get to focal point modeling. Monica, yes.
It's me. I was just wanting to remark on the flexibility of this anchor modeling.
Yes. It's fantastic in that scenario. There's very little things. Now, Veronica, the thing, I'm glad you reminded me, lately, the database vendors, for example, SQL Server and that, have done so much on designing the access plan to data that the issue of denormalizing for performance is dropping away. And what they can do with these access plans is that they can actually jump tables to get to the data that you need. So if you are asking about events for a program, okay, they find the quickest path, and they can remove all of these. Remember, they call them a cross join, where they'd load every single data element into the database, and that would cause the performance. Now, the latest techniques are they're not loading all of it into the database, only the data that is required. Okay, so they're overcoming those challenges that normalization created and why we led to denormalization. Okay, they are overcoming a lot of that. Okay, now we go to focal point modeling, and here's what focal point modeling is all about. It's called unified decomposition. So for an entity, you would identify the core concepts, what are the most important concepts, and you can see this is in orange. And then they build what's called an ensemble, which is the other entities that make up that core entity. All right. Now that ensemble is almost a packaging technique. And think about that data vault modeling. These can be your satellites and sort of your non-core, like an address. Okay. So typically when when business people talk about customers, they talk about the customer and they assume that you know that address is part of a customer. Okay, so almost an address is what we call a second-class citizen. It is not as core as a customer or a product. Okay, and it's very important to know what level to go down to your entities and decomposing this thing. And then what they do is that they reconstruct the dimensions from the ensemble. So entity breaks down to ensemble and works together as a package, and then it's reconstructed to a dimension on the other side into your dimensional modeling. Okay, then we've got fact-oriented modeling. So this is what's brought out in terms of, and this is also in terms of ORM. But what I love about fact-oriented modeling is you actually start with asking the business about the facts in the business. So who are your providers? Okay. And then where do they travel? And what is the transport airplane code? So what you're seeing here is a representation, not just of the entities, but of all the data that's involved in this model as well. And that's very helpful for business people when you present this, is that they can read through it and say, well, does this make sense to me? Okay. And it's a nice way of modeling. They don't get into abstraction and all these funny things. They listen to what the business people are. They call it a universe of discourse, meaning the communication that we're building. That's the universe of discourse that they create. Now, I've done a whole lot of comparisons between ORMs and ERMs and UMLs, and it's helpful to go through, but we don't have time now. When you get the content, you can go through all of it. Okay. So again, there's ORM2 or FCOIM, and these are the different ways in representing those two different ones. So notice the textual annotation of the model elements, and that's what I like about FCOM. You can actually read it. You can read it and say, does this make sense? So there's a nice level of validation around those models. Okay, and a nice way of describing it. Okay, so lots of different details and examples of FCOIM. Okay, now time-based modeling, and you can see focal point modeling. That's there. Let's go to NoSQL modeling. Okay, now can you see here, Paul? This is a conceptual map of all of the data elements. We've got user 1, their name is Joe Doe, their age is 40, the thing is gender, and this is what it looks like in the JSON document in the database. Okay, so there's no real conceptual model. We would sort of handcraft this to discuss it with the business, to explain to them what there is. And another thing we would do is you can take an existing ER database, a relational database, and you can create a JSON document from the relational database. And you're seeing lots of these converters that read a relational database. They create a JSON document for the actual application to work, and then when it comes back, they store it into a relational database. I'm not sure why you'd want to do that. I'm not sure, why don't you just use MongoDB and you store the JSON document away in the MongoDB? And the nice thing about that is, let's say something changes and I want to add a new attribute, for example, on billing. Okay, let's say I want to add the CVV code. Okay, I can't do it here because I have to go and change the table definition. But in a JSON document or a MongoDB, all I do is the next document, the next time I store it, I just add the CVV code, the CVC. So I don't need to talk to any DBA. I don't need to ask permission. As a programmer, I just change it. The problem I have is that then no one really knows what's in the database. Okay, and not many people can go and query these databases using SQL. So what they do is they actually install tools like Idera on the database system, and they reverse engineer it every night to say this is the data that's being stored. So this is almost a virtual representation of the JSON document. Okay, and this is sort of how the documents are stored in the database. there's a database, then there's a collection of documents, all the documents that have this similar structure, and this is the way you would write the JSON code. db.products, which is at the collection level, find. Okay, a quantity that's greater than 4. And it comes back with an ID because that quantity is 50, and that's the document that it comes back. It returns the document to you. So Paul, can you see, does this help you understand the JSON document?
Yeah, thanks,
database?
Yeah,
okay.
Thank you.
So it's stored as one big blob. There's the data that's written away in the blob. And when I read it, it comes back out again. What is the nice thing about it? It doesn't have to go and navigate all these different tables and bring it back. It's almost one IO in and one IO out.
Yeah.
Okay, so very helpful in that way. And then we have the other format that comes about, and this is what's referred to as a knowledge graph database. And the reason why it's a knowledge graph database and not a property graph database is because it contains metadata. And you see country. So USA has a typing. Can you see this metadata relationship that we have? And here as well, Da Vinci is a person. Lily is a person. James is a person. Okay, Mona Lisa is not a person. Mona Lisa is a painting. Okay, similarly to the Louvre. Okay, it's a museum, and Paris is a place. Okay, and so this is what's referred to as a knowledge graph. Okay. All right, semantic modeling. Okay, now this is, it almost doesn't have a physical storage. Okay, and you can see here, this is what it looks like, and it's all basically a model of the concepts and the relationships between the concepts. So there you can see food. Food has a component. So I'm not sure how many of you have ever worked in a recipe or a food business, and they have basically the bill of materials, what makes up a food item. So you can have an aggregate food, and it's made up of sugar or zinc or ammonia or amino acids. Those are components of the food, and it's given a name, and it's a food group, and there's a structuring. Okay, sorry, Andrew, I've just seen it now. How would you actually know which model to use for which kind of scenario? Andrew, that's a great question. And remember, and I'll go back to it, there's you need to understand the type of data that the business needs. Okay, what type of data? For example, are they working with documents, unstructured storage? Okay, if they are working with unstructured storage, please don't use the relational database. Okay, if they are working with documents that need to be brought into and interpreted and ingested, you would typically use a graph database to store the contents of a document database that's all broken up. It's been broken up into the individual elements by subject, predicate, object. Andrew, does that answer your question?
Yes, makes much sense, Harold. Thanks.
Okay, fantastic. So step number 1, what type of data do the business need to make decisions on? And then what's the best storage mechanism? Now, if the storage is a graph database, then you probably want to look at using a knowledge database or a ontology that describes the words in those documents, or you store it as a blob. Or, Andrew, if you have a image database, if you have a set of images or a set of videos, you probably go for a key value pair. Okay, where you don't really want to know all the different elements of that video. You store it as a blob and you can retrieve it as a blob. When you want to look at the language items about subject, predicate, object, then you want to go in a graph. Okay, so please pay attention to the business requirements. What data do they have and how they want to store it, and then what analysis. So what you would also do is have those inference engines on being able to make decisions based on the data. Okay, and a knowledge graph is really good for that type of scenario. Okay, so now going back to, let's go to the conceptual model and try to No, I don't know why that got there. It's not going to where I need to go. 136. And then, okay. Sorry, 137. Okay, so let's look at the real world challenges. So the first thing that we get into defining accuracy. Now, if we were able to achieve this modeling manifesto, this would almost be the ultimate accuracy. We make a change to the model, okay, and then we generate the system. Now, this is quite interesting because I'm not sure how many of you have used data virtualization. And that's a very powerful technique where you build a model and then you say to the virtualization engine like Denodo, here's my model, and this is the link to the different databases, the underlying databases. And when you get someone querying the model, it issues the query to the underlying database, brings the data into the virtual data model. Okay, so that data model is all sitting in memory. And when you switch it off, it disappears, but you can then do a change to the model, bring it back again, and then you see how that works again. So that's very close to a conceptual model. Okay, but it's not generating application code. Okay, so data virtualization is a lot easier because it doesn't have to generate application code, but it does have to generate the ability to integrate data from the sources. Okay. So it would be nice if we could generate a system. I think that would be a whole lot easier for us to test because we could generate the code and then test it, use a user interface and test it. And there it is. Has this conceptual model worked? Yes or no? Quick to visualize. Okay, but we don't have it. So what we need to do to measure the accuracy is we need to build a set of scorecards. Okay, so we should have a scorecard for a business definition. Is that business definition correctly specified? A data modeling scorecard, a data flow scorecard, a business process scorecard, a user interface scorecard, and a model-driven development scorecard. And there you can see, and I'm going to give you some examples, but a data flow scorecard, you remember the data architect, they design the way in which the data should move in the system. Then you go to the data integration team, and they go and implement the data lineage and implement the data flows. What we need to be able to do is to say, once you've implemented, how well does that reflect what was designed by the architect? And there's a process called stitching, and you'd actually compare as designed versus as implemented. Okay, but it's not easy to do that. But I can show you here. This is our data modeling scorecard. This was developed by Mr. Steve Hoberman, and you can see this is what I do. We build a relational model, conceptual model. I run it through the scorecard, and we present certain results. And here are the rules. Okay, so the rules in terms of requirements lifecycle, priorities. These are the rules that we have, and almost the negative marking system that we use to build that data modeling scorecard. If there's anyone who would like to see an example of that, happy to share. I've got a whole Excel spreadsheet of these models of all those business rules. This is what it looks like here. Can you see my data modeling scorecard? And it looks at correctness, it looks at completeness, the model scheme, the structure rules. These are all the rules that you use to mark and score a model. Okay, that's the level of detail you need to go to get this model accuracy. Maybe just to pause there and ask anyone if I have that question. Can you see that we shouldn't just try to have these peer reviews where people come into a room and then argue about the model? Okay, those they can be quite detrimental. And then you typically listen to probably the most experienced person or the highest paid person in the room. You need a lot more formal way of looking at the accuracy, and you must do your homework before you get into those reviews. Are there any questions on that data modeling scorecard? No? Okay.
Just to say, it's nice to see a detailed example there on screen at the moment.
Yeah. So those scorecard results are pretty important, and it's really helpful to show people how you got there. And then what is nice to do is you have all of the comments to say people, you can go and do the scorecard, and then they must go away and fix all the issues before they come back again. Okay, so it's helpful for them as well to get that right. I also do it in Power BI. So you can then measure, are we getting better at data modeling? Are our data modeling skills getting better? Or are we having the same problems over and over again? Okay. Now, data models are one of those areas that have a great impact on lots of the other domains. Reference and master data, all the domains for party domains, party, product, finance, we need data models. Taxonomies, hierarchies, we need data models. Data integration, the canonical model is great. The data virtualization is a great technique doing that. Data storage, we build a model of the database schema, the data dictionary. Data warehousing, data vault, self-service, data science, wide data sets, feature engineering, and then metadata. Okay, so we have a meta model per model type. So we have types of models for reference data, types of models for integration, types of models for storage. Now we need to have a model type per model over here, and then we need to bring them together. Why do we need to do that? We need to do that so that if we change something, let's say we have a business definition change, that means we may need to change the taxonomy, we may need to change this, we need to be able to understand what are all the models that change, and that's what the unified model does. It links these models together so we can do proper impact analysis. Okay, so conceptual modeling playbook, we should have a policy for modeling, we should have an implementation framework, we should then have the SIPOC, which is basically the procedure that's used to create the output, who supplies the inputs and who consumes it. Okay, by deliverable, and then a scorecard. We need these scorecards that I showed you previously. Okay, now here's an example of an implementation framework. I like to do all of this planning at the data architecture level. Okay, because data architecture is going to tell you when and how the data models need to be designed, and not just the data models, but the meta models, the sort of discussion that Don was talking about. How do we bring in all of these meta models and data models, and then how do we integrate all the data into there? How do we share the data? How do we flow the data? So data architecture is the right place to build the implementation framework for data modeling. Okay, and here's some details on basically a SIPOC for or implementation framework for data architecture. Okay, get the requirements, understand the type of data. Can you see here, Andrew, what data types are we working? What are the risks? What does the data landscape look like now? And then you go down to the platforms and the data solution that you built and the integration and the hub and the data product build. So here's the whole flow of putting your data architecture together. Okay. Best practices for conceptual modeling. Make sure you understand the objectives of that origin, of modeling the origin. Get the right stakeholders. Make sure you've got the right and appropriate notation that you're using. Okay, do you need to describe processes? Do you need to describe data, user interfaces, application logic? What is it that you need to write and compare here? Written and visual representation. So the concept map is great for business glossary, written definitions, and then the conceptual model for visual presentation. Focus on the core. Have the metadata being accessible. So once you create this model, can people clearly and quickly see a model of the data, and also use for lineage and impact assessments? And then how do we model validation? Fact-driven. That FCOIM is a great way for business SMEs to say, yes, this model makes sense. If I read the facts of this model, it makes sense to me. Okay. Now, this is what I refer to as decision science or the advanced techniques. How do we build a decision, making decisions? What are the elements of a good decision? And then what are the right quality of ensuring decision making in business? Not rock, paper, scissors. Okay. All right, so here are the key aspects of decision modeling. Okay, how do we represent the decision process? Okay, how do we handle uncertainty in decisions? How do we look at behavioral insights? Who's making the decisions? And this one was for Don, and I'm really sorry he's not here in terms of the methods. Okay, now can you see there's some really powerful methods of this decision making? Decision trees, they give you a graphical representation of the decisions for a specific process of decision making. Influence diagrams, relationship between decisions, uncertainties in your data. So if I'm not clear, if I'm not convinced that my data is showing me the right thing in terms of cause and causation and correlation, I may be uncertain about that. Okay. And multi-criteria decision analysis, conflicting decision making. Now, this is what's important about being able to show all of the different elements of a decision, what makes up a decision, so you can see where your weaknesses lie in decision making. Okay. All right. So that was basically the end that we got to, that advanced analytics. So maybe just to go back to, sorry. Okay. All right. Any questions on, I think, sorry, I went a bit late on this. There was a lot more detail for the professional in terms of actual examples. Are there any questions that anyone would like to ask? Martin? Adam?
Yes, thank you. It's really good and very detailed going through all those. My question, I suppose, is about dimensional modeling, because that's the one that I'm not clear when and why you would use it. So do you have can you give a concrete example of why you'd use that over something else?
So this is your data marts. Remember Kimball, the data marts that we build reports on top of to help us with that, what they call descriptive analytics or BI, business intelligence. When we talk about BI, we use dimensional modeling for those data marts. So Adam, think about this. It's almost like a pivot table in Excel. And let's say you bring a date dimension, you can draw from what is the sales per year, per month, per day. So it's a way of aggregating your data to these high levels and then drilling down to understand the details. So it's all about data mart. Dimensional modeling is for creating data marts. Does that answer your question?
I think so, but it's
not really.
To me, it almost seems a way of just how you'd construct a query.
Okay, so let me show you here.
Your kind of
relational
data behind it.
Yeah. So let's look at the data vault. Remember, we have our applications, the data vault. We bring the data into staging, and then we bring it into the data vault. Okay, and we do integration here. Now these information layer, where the BI reports, the dashboard sits on top of. Any BI report sits on a star schema or a dimensional model sitting in the information layer. So these are very well-defined facts about sales, order, whatever it is, and they are very controlled data mart that's used to present the information. And you use dimensional modeling for those data marts.
Okay. Thank you.
Now your queries, when you're talking about, if I was to sit there writing database queries to do more detailed analysis, it would typically happen at the business data vault level, because the star scheme is very much in terms of it's a difficult one to write queries on, because there's so many surrogate keys and links and dimensions and stuff like that. So you would typically write your business queries against the business data vault and not the fact tables.
Okay, thank you.
So your business data vault looks a lot more like a relational diagram, where you saw customer linking to an account, linking to that. And that's the sort of level that you are doing. If you're doing ad hoc investigation type of database queries, it's easier to understand the data when you're working through a relational database and not a dimensional mart. Dimensional marts are there for performance. They want to give you the answers back as quickly as possible. The business person does not want to wait 5 minutes, 10 minutes to get that answer back. So all the numbers are aggregated along these hierarchies. So if I go back to dimensional modeling, when you build a dimensional model and you load it up into a data mart, they've actually got all of the numbers of orders aggregated at a year level, a month, a country, a region. So when you say, what are the sales, what's the gross sales amount for year 2024, the number's already been aggregated and gives it back to you instantaneously. It doesn't go and write a SQL group by to give you the numbers at those different levels.
Great, thank you. That makes it much clearer.
Okay. Yes, Martin. I thought you were going to ask a question. I'm not sure. Okay, maybe not. Yes, I'm not sure. Anurag, is that the name, or is it Kunomaru?
Yeah, that's my name. I have one question related to data science and AI. What would be the best model that would suit on this aspect?
Okay, so depending on the type of analytics that you're doing, you would use a different type of model. Okay, so maybe just to share with you, when you're doing inferences and you're trying to infer information about the food, right? You can follow this graph all the way around to help you with the inference in terms of how many units were used to make the food. Okay, so depending on whether you're using logical inference of information or deduction of information, you would use a graph database. Now, for example, the LLMs, they use this type of graph database, but they use vectors to describe the distance between this word and this word. Okay, and they use a vector database and a graph database to strip all of these elements together and connect the words together and the strength of the words between each other. Okay, so that's what's referred to as a vector database. Does that make sense?
Yes, please. Thank you.
Okay. All right. So the LLMs are all about statistical vector relationships. Okay. When I'm typing a word or I'm typing a sentence. So, for example, if I go onto, let's go onto Copilot in that situation, just to share with you. Okay, if I go there and I type, when you're typing things like is a conceptual model, what it's doing is that it is building a statistical model of everything that I write here. It takes these words and then interprets the LLM using the different words that I've provided here, and it sort of knows what is the next word that's related to conceptual data models. Okay, so it builds these relationships between terminology, and then it builds references. So it actually, the way which it's building up these sentences is when it ingests all the data from all over the web, it builds relationships between the different words and the strengths of the relationships by means of a vectorization. I'm not sure if I explained that properly.
It makes sense. Thank you.
Okay, so it's almost a proximity algorithm in terms of what is the proximity between the different words, or future modeling and conceptual data modeling. And so when you ask the question, it's going to link all of these terms, but now by means of a proximity or a vector, the distance between them. Okay, so that's very much what is stored is the relationship between these words and terms. And that's how it can almost forecast or tell you what the next word is that you're going to type. That sort of IntelliSense. It's because it has relationships between words. All right. Are there any other questions? Mr. Bolton, do you have any?
No, just actually more of that slide where you've just just really brought together with where the modeling touches the different areas, the different knowledge areas, like
yes,
master data, the warehouse.
Right.
I just really enjoyed that slide because it just again just and some of the scenarios I'm talking about where clients are saying we're not doing data modeling.
Right.
And just thinking that, model compatibility, that's just a fantastic view.
Yeah.
Thanks for that. They're more of a comment than a.
Great. And then also for another one in terms of data science, I don't know if you've ever heard of these wide data sets. Sorry, Paul, I'm going to come back to you.
No?
But a wide data set is when they're trying to look at feature engineering in terms of or goal seeking. They start off with feature engineering, and they basically say, to achieve a specific outcome, what are the dependencies of the different columns in this wide data set? So a wide data set could be something like 2,500, 3,000. Google has these amazing wide data sets that you can analyze behavior of people. And what you're trying to do is to say, to achieve this outcome, that column, that feature, and that feature are related to each other. Now, what we should be able to do from a wide data set point of view is from our data marts. Remember, the data marts have all those dimensions and facts. We take basically every attribute in every dimension and in all the fact tables, and we just make one big table of everything. And now people can start comparing the age and the gender to the year and the product and the region. All of these things are in one massive data set, and they can start relating the different elements to each other. And that's what's referred to as feature engineering. So that's another thing that they use in data science when they're trying to understand relationships between different columns. So Paul, a lot of data modeling and integration across all of these different areas are used to bring everything together and to create an environment and to structure the data depending on the type of analysis that you need to do. Okay. So different analysis, for example, inferences and deduction must be in a knowledge graph. Now, a knowledge graph requires an ontology. Okay, so you need the taxonomies and ontologies for that type of scenario. If you're going to be aggregating in terms of numbers, in terms of how many or why or probability or things like that, you've got to go from unstructured data to tabular data. Okay, so you've got to bring all the data and you've got to bring them back into Excel type sheets. So you can sum and average and mean and median and stuff like that. So yes, it's nice to have all of these fancy NoSQL type databases, but to do analytics on top of it, I've got to re-engineer a rectangular shape that represents the data in these no document databases. So no document databases are great for storage, for I/O operations and things like that, but you need to do some work on them to get them back into an analytical shape that you can now start calculating.
Awesome.
And of course, metadata is what data is sitting where. Where do I find this data? What does the data mean? What is the format of the data? That's all metadata. But that data is defined by a data model. What is the structure? What is the meta model of that data?
Okay. Awesome. Thank you.
Great. And I suppose the one I've missed out here is basically the business glossary that should be in the metadata, because that word map that we're talking about is also fundamental within this.
Now, when I saw the JSON example, I was just trying to see how, because it's something that when you're talking unstructured coming in, and how would you ever use it if you don't bring some structure to it?
Right.
It's trying to read what is it called in that column so that you can map it to something that's common language or the business glossary, right?
Yes, correct. So Paul, if here's this thing now, this type of format is really nice for taking out of the database and giving to the application so that they can present on the screen. Right,
Yeah.
so they can present there's Bob Jones and his date of birth and his billing. Really nice way of moving the data from the data storage engine to the front screen. But when you want to start calculating, for example, how many Joe Smiths do we have, or Sam Smiths and stuff like that, you got to get all the documents together in a single database. So these documents live independently. Okay, now you want to calculate the number of contacts we have. And what is their number into how many Smiths contacts do we have? Okay, we've got to get it into tabular format so we can start aggregating and calculating. We can't do a lot of it there. Now, whether that's done underneath the covers or whether that's done by integration, that's up to us. So this could certainly be a virtual data model on top of a JSON database. That's where it's really powerful to build data virtualization. It's almost unpacking all of these blobs of data into something that we can do calculations on and do queries on. Adam, does that also help you?
It does, thank you. It's good to see and go through concrete examples.
Yeah.
Of exactly why you'd use something over the kind of more a different choice.
Yeah. Now, to give you some background, it was actually, I believe it was Amazon that created the JSON format. And Adam, they were suffering from when you did a query on a product or you're looking for a product, there was so much information that they were trying to get back to the user that they couldn't be that as efficient as Google. Okay. Because they were navigating relational tables. So what they did was they said, we want to change this. We want to kill the number of IOs, because typically a relational database would have an IO for contacts, an IO for billing, an IO for customer, IO for connections, and IO for purchases. So you'd have 5 IOs here, and this is 1 IO. So I'm sure you can quickly see that when you have a database like Amazon of all the products and all the customers and all the also recommended, also bought, also did this type of stuff, that's a massive relational database, and they were dying. So they said, no ways, we've got to stop that. So basically what they said is they built this thing of one screen relates to one document. So when I ask for the information on the screen, it's going to go to the database and it's going to come back with one document. And it worked really well in the beginning. And then what happened was, as they started to grow, they sort of, this JSON document became too big. I think they recognized the problem when it was getting to about 3 gigabytes. One JSON document for one screen was 3 gigs big. So what they then did is they actually broke up the JSON documents and they created document linking. And then they would load it, they would have partial loads into the screen because they were dying. But they're still performing a whole lot better than what the original relational database does. Great. And the other thing, Adam, that we do is in our data modeling course, for example, Craigslist. I don't know if you know Craigslist. That's the thing where they sell your cars and your vehicles and everything that's on there. You know, something Craigslist. Now, you have no structure on what is required to describe the item you want to sell. Okay. And they would typically have that as a document database or a key value pair. So you could store images, you could store music, you could store whatever it is there. And you just had a single key that you found and located that image and then presented it on the screen. So those are difficult databases to work with. A relational database that just doesn't suit that need. You don't have that fixed structure to be able to create that. I wonder if Andrew's around. Andrew, does that also make sense to you in terms of answering your question? Okay, maybe not. Great.
Cool. Thank you, Howard.
Thanks, everybody.
Yeah.
So, thanks.
Thank you so much.
Thank you. It's particularly interesting today.
Thank you.
So, yeah.
Thank you.
Thank you.
Cheers,
Thanks,
everybody.
that's great.
Thank you.
Thank you, sir.
Bye.
Bye bye.
Bye.